And welcome back. Yes, I've done it again. I have a flashing LED on my workbench, and it's particularly pertinent to Arduinos and all MCUs everywhere. What could that possibly be? Well, let me turn the lights up first, because it's a little bit dark, isn't it? Let me get those lights on. Alexa, turn on workshop lights. Oh, and there I am, sprung into action. Right, okay. Now, this little breadboard here, as you can see, has a chip in the middle, and if you're really sharp-eyed, which I'm still not, you can probably see it says 555 on it. A 555, I hear you cry. Surely we've moved on since then. Yes, we have really, but remember the 555 has been around for I don't know how many decades now, probably what, 5 decades, probably in the 70s was it made? I don't know, I've been using it for so long, but I've stopped using it for probably, what, 10, 15 years, something like that, because, you know, a tiny little AT Tiny 13 or 85, whatever, would do everything that the 555 can do, and a whole lot more. So I was just browsing the internet, as one does, following various links and what have you, mainly for the that dimmer fan thing I'm looking at, SCR, whatever. And this little thing came up and it said how to avoid latch up on an MCU. Well, it's not really latch up I'm trying to stop. Where latch up is where a device gets its knickers in a twist basically and turns on and latches on and cannot switch off again. And the only way to reset that apparently is to power off. And then, you know, power cycle basically. So turn the power off, turn the power back on, and everything's okay. Even on an MCU, the Watchdog Timer is not sufficient. Reset doesn't work. So basically, this circuit was promoted really in the article that I read as saying, look, sooner or later your MCU will hang. For whatever reason, you know, electrical interference, whatever, and maybe your Watchdog Timer is not enough to get it started. And I thought, 555, forget it. We've moved on since then. I'm not interested. Where am I? Because 555s do have a place in my heart from years gone by. And I thought, well, let me read a little bit more. Now, towards the end of the video, in fact, right at the very end of the video, there's a little thing that I've dropped in that somehow calculates where your next holiday could be. Yeah, I know. I'm not going to tell you any more. It's right at the end of the video. If you want to jump to it, it's in the description below on one of the time stamps. But I just thought I'd tell you that to let you know that there's something at the end. It's very clever. You can do it with your kids as well and see if they can work it out. Right, that's enough of that. Let's get back to the main video, shall we? So let's just have a look at the article that I was reading and why I got interested after this quick message from my sponsor. Let's have a shout out for JLCPCB, manufacturers of top quality PCBs. I'm going to show you today the options for SMT assembly. And there's a special offer on at the moment. There's no engineering fee, you just pay for the components used. Here's a recent example PCB that I had assembled by JLCPCB. I've been assuming you've got the board all set up like this one. All you need to do is generate 3 files. You need to generate the Gerber files by clicking on that one up there. So you click on there, it says do you want to run a DRC check? You should always do the DRC check just to make sure everything's okay. And then down the bottom here it's generate Gerber. Click that. Say where you want them to be saved, make sure you can find them, click save, and you're away. That's the first set of files. The next file you'll need is the bill of materials, the components list basically. Click on the BOM at the top, and that will export a CSV file. Ideally, keep it in the same place that you had the other one. So export BOM, and save it in the same place. The third file you need is the pick and place file. So go to the menu here at the top, scroll down until you see export pick and place file. Click that. You do not need to mirror the coordinates, just leave that as it is and click export. And once again, save it in the same place as you did the others. Now you've got your 3 files, you're ready to upload your files into the JLCPCB website, quote now. Once you've reached this page, add the Gerber files, which is the first set of files that you actually generated. Fine, there's the PCB, but remember, we want this assembled. So scroll down the page until you hit the SMT assembly. Click that. And it says which side you want to assemble. Well, on this board I've only got components on the top side, so we'll click that one and confirm. Here it wants your 2 other files that you generated. The BOM file, bill of materials, that's the components file, and what it calls the CPL file, that's the pick and place file. Add those 2 in exactly the same way, confirm, and you're away. Here you can see the board that I uploaded, this one here, and the assembly request here. And that's it. Now it takes about 3 to 4 days to actually generate the board and assemble the components. and I tend to use the DHL shipping method because it's the quickest, but there are multiple options available to you. And there it is, very simple and easy. How can you go wrong? Try it now. Right, this was the website that had the article on it, well, the Google result, you know, so if you scroll down a bit, here we are. Now here's the actual circuit. So we've got a 555 in the middle, a couple of MOSFET transistors, which is one of the things that sort of piqued my interest. I thought, hang on, that looks like the arrangement that I've used many times in the SI4599 for automatic switch off on kill circuit. There's another MOSFET over here to drive something or other. I thought, okay, this looks a little bit more interesting now anyway. So I carried on and read down below, and it says, well, this is actually a free circuit from Elector magazine. So let's whiz over to that and just see if there's any more information about this circuit. Right, so this is the main article then in Elector magazine, same circuit exactly. And credit has been given to, who wrote this? Let's have a look. It is in fact Wolfgang Borst from Germany. Good old Wolfgang. Anyway, so that's the circuit I started off with, and I thought, okay, I like this arrangement at the end to switch an Arduino on off. We've done it before, as I've just said. So I thought, I could use an SI459 at the end there, and I've got quite a few of those hanging about. Okay, you've got an IC here that is an astable of some kind with a trigger. Right, here's going to be a quick circuit diagram then of a astable free running oscillator, which is what the 555 is good at. Now, free running means that it will just keep oscillating and producing a square wave on its output on pin 3 like that, and that is dependent totally on the combination of resistors here, here, and the capacitor, normally electrolytic but doesn't have to be, that is here. Right, so in our particular circuit we've got a 10 microfarad here, something like an 820k here, and a 120k, I believe. Don't take my word for it, you'll have to go and have a look. So this is producing sort of a 5 to 10 second square wave here, but of course by adjusting these values you can make this run at audio frequencies, and that's great. So pin 5 is simply a decoupling sort of pin really. Pin 1 goes to ground anyway. Pin 4 and 8, that's timer and VCC, go up there, and that's it, that's your circuit. Now this is astable mode, free running, so it just keeps producing this output on here regardless. The 555 can run in two other ways. It can run in bistable mode, which means you'll need a different signal on the trigger pin, which is pin 2, to make it flip-flop from one to the other. And then there's monostable mode, where you give it a pulse, it switches on for however long you've set these components for, and then flips back again and stops basically until it waits for another pulse. But those are all things you can find out. I don't know, I'll put a link into, I don't know, Wikipedia or somewhere. There's loads of stuff on it there, but this is basically how we're running this chip to run it in freestanding. Now what happens is, of course, is that the charge builds up on this capacitor here so that it turns on, creates the pulse, and it turns off again because this now is high enough, the voltage is high enough on here that it discharges and stops on the output. However, if we were to create a switch, for example, on here, if for example you put a switch here to ground and press that every so often, it would discharge this capacitor and never let it get to this point here and therefore switch off. It would just stay on all the time, which is effectively what our circuit is doing. Okay, you've got an IC here that is an astable of some kind with a trigger, and a MOSFET here that brings the trigger to ground if it's fed a suitable value in here from an Arduino, say. So it's a bit like, we almost did this before with the auto switch off, but what this requires is a pulse from the Arduino every few seconds, and with the values of the components, and it's up to every 10 seconds. I've shortened it on the sequence on my breadboard just to make it a bit more visible in the demo. But basically on here you get a pulse come in from an Arduino. This bit here, we'll talk about this in a bit more detail. This turns whatever you've got on here into a very short pulse that then turns on the MOSFET. That brings pin 2, the trigger, well, this capacitor, to ground, thereby shorting out this capacitor. So it doesn't trigger, it just stays on at this point here, because the output pin 3 drives this N-channel MOSFET, which then drives a P-channel MOSFET, and your Arduino is powered here. Great, and as you know, the SI4599 can take an awful lot of current, something like 6 amps on this P-channel, so that's more than enough for our Arduino use. Now what happens then is if you don't supply a trigger here in time, the astable is building up the charge on this capacitor, and once it reaches a certain value, something like 3 volts or so, it goes right, blink, and it flip-flops. Okay, so it flips to the other state, which means that this then goes off. So if this was connected to an Arduino, the Arduino would at that point die, and anything else that's connected to it and powered from the same line would die, just as though you'd gone to the power switch and pressed off. Okay, and after, I don't know, a few seconds, I think he mentions 5 in here, but as I say, I've adjusted the timing, it all springs back into life again. I thought, this actually has some merit. I didn't understand all this bit down here really, because I thought, why are you turning your pulse from an Arduino into a really tiny pulse? And we'll look at that in a bit more detail. Right, let's just go back to the workbench, because we need to look at the multimeter, voltmeter part of it, and the oscilloscope to fully understand what's going on here. So back to the workbench. Okay, right, now it's running away, that's fine, and the reason it's flashing the LED is because I haven't emulated the Arduino giving a pulse. That's what this little switch down here is for. If I press that switch, as you saw, it suddenly sprung into life there. That switch is a bit like the Arduino giving a pulse in. As long as I keep pressing it every few seconds, that LED will never go off, and the LED represents the Arduino, of course, the power out. So as long as I keep pressing that, or supplying a signal from the Arduino, of course, then that's fine. It will never power off. But as soon as you stop pressing the switch, or of course the Arduino giving a pulse, because things have hung up, it's gone off and it will recycle. Right, let's put the multimeter on there so you can see the voltage across it, across the capacitor. Now, as I say, I've changed that capacitor there at the back. You can see, I think I've got like a 3.3 microfarad capacitor. It should be 10 according to Wolfgang's circuit. But so this might I wouldn't recommend having it quite this quick, because if you're doing a lot of stuff in the Arduino and perhaps, I don't know, waiting for an input or something, 10 seconds can go by pretty quick. But just for demo purpose, this is fine. Right, let me get my probes, stick them in this breadboard, and I'll be right back. Right, the multimeter is connected up across the capacitor in that circuit. That's this circuit here. So what we're doing, putting the probes from this point here and ground, so down here. Because if the charge on here builds up sufficiently, the 555 will flip to the other state and turn things off. So as you can see here, it's building up to 3. Once it's about 3.2, did you see the LED go off there? Okay, and back on again when the capacitor is discharged enough. So power's off, this just charges down to about 1.7 and flips back again to the on state. Now that's great, and as I said, if I keep pressing this button here, you can see that the capacitor, let me do it with this hand. So if I keep pressing this, as you can see, the voltage on that capacitor stays nice and low. So it's never going to flip to the other state and turn the power off. Great. Except, let's have a look at the oscilloscope. Now let me bring that in first. Right, so what you've got here on the oscilloscope is a lot of noise, that's for sure. I think it must be the environment actually where I'm working, because that much noise I most certainly did not get while I was researching all this. But just ignore that level of noise, that's not what we're after. When I press this switch though, watch what happens to the trace. Now you see that spike there? That was the button giving a pulse, and it's shaped by the capacitor and diode, and we'll talk about that in a bit more detail. However, I'm thinking, alright, so every 2 or 3 seconds the Arduino gives out a pulse, and it keeps the voltage over here nice and low so that it doesn't switch off the power. But the Arduino, of course, can go around its loop thousands of times a second, and you might think, well, every time I go around this loop, I'll just issue a pulse for, I don't know, a millisecond or 2. So you can imagine how many pulses there are going to be. Now you watch what happens. First of all, watch the voltmeter and watch the trace on the oscilloscope over there as I press it very, very quickly. Nowhere near as quickly as what the Arduino could do, of course. So there's a pulse. Now if I press really quickly, oh look, where have all the pulses gone? They're tiny little pulses. The voltage is increasing. Oh, and the voltage has gone off, even though I've been pressing this a lot. And I think that's a problem with the circuit, really. If I go back to the circuit, the problem here is that this part of the circuit here is taking the pulse in here. So imagine that your Arduino has suddenly gone high. This capacitor charges, puts a single very small pulse on this side. This diode is in fact the wrong way round. Well, I think it's the wrong way round. I don't see why it should be that way round. You'd be shorting the signal to earth. So I've turned this round the other way. This resistor is required. That's what keeps this MOSFET off until it does receive a pulse. But having received a pulse across here, and you might have seen a similar arrangement to this with the capacitor on the ICSP boards for, well, all Arduino type circuits, so that you can issue a quick reset as you saw on the scope. But what this is doing, it's making it so quick that the MOSFET here barely switches on for any time at all, and most certainly does not discharge this capacitor to ground via this circuit here. So we don't really want this bit, well, that diode, that capacitor and that resistor, I do not believe are necessary at all in the circuit. Not if we're going to be using it with an Arduino, because the Arduino, as I say, can say, here's a pulse for as long as you want. Okay, and I'm not talking seconds here, we're talking a few milliseconds, aren't we, right? Maybe, I don't know, let's just pick a number out there and go, look, here's a pulse for 5 milliseconds. Okay, that's enough to turn this MOSFET on, discharge this capacitor, end of job. It won't switch off the power. So if I were to use this, and believe me, I'm tempted to make this up on a little PCB, I would not have these 3 components in here at all. We don't want a short pulse so short that this capacitor has already charged up and doesn't deliver that pulse anymore, and therefore cannot discharge this capacitor. So what we're going to have is this connected up without those components, so we get a nice long pulse. Well, for as long as you hold effectively the trigger down on this button here, but basically as long as the Arduino is pulsing high, digital right, high, this MOSFET will turn on, short all this to ground, and then you can switch off. And as I say, I reckon 5 milliseconds will probably be more than enough. Let's have a look at the circuit diagram that I've put together on my CAD program, just to see how it looks now. Right, this is the circuit then that's slightly modified. We got the SI459 as the output over here, just a 3-pin there for voltage in, out and ground. That's the configuration of this device here. Do you know, I hate it when they just give footprints like the physical device. I don't think this is very helpful at all. Yes, I know I should have created my own footprint. Do you know how long that takes? It's a pity they don't, you know, put the actual, well, this basically in here so we know what's connected to what. It's easy to make a mistake, believe me. So anyway, that's why I put this little image up here so I know what's what. So that's the output driver, and you know how tiny that little chip is. That's the same one that I've used on my smartphone charger. In fact, I'll show you that in just a sec, just that little chip area. 555, well actually these days it's quite big, isn't it? Because it's an 8-pin and same size as an tiny 85. And talking about SMD components, it's quite big, but there we are. So just a couple of resistors. This determines the mark space ratio along with this capacitor here, and it's to say 10. As I say, I'm using a 3.3 in the demo. That's just for stability. Some people don't put this one in on pin 5, but I've always done that. There's a decoupling capacitor here. Now if you've seen my Bacon Bytes thing on capacitors, it's 100 NF, and whilst it's physically shown over here to one side, really it's got to be, you know, very, very close physically to the chip. In fact, it does show it on here. If you can see on here, if I hold this up to the camera, there's the decoupling capacitor, that one there, and there's the chip. So it's right across it on the 2 power legs. So yeah, that's what you need to do. Well, you know, when you create a PCB or whatever Veriboard, strip board design. Right, back to the, no, that wasn't it at all. Where were we back to? We were going to PCB design. There we are. Right, so here's the MOSFET that shorts this capacitor to ground. Yes, we need that one there. I've shown 2 here because one's SMD and one's through hole. But in fact, I don't think we need these capacitors. Well, that capacitor, that resistor, and the diode of your choice here, SMD or through hole. I think I'm going to dispense with those, kill those entirely, and yeah, just keep that one and that one. Well, one, it keeps the component down now, and B, as we saw, too short a pulse on that input caused by this capacitor not being able to charge up quick enough will not cause this to switch on, and therefore this capacitor will not be discharged. So that's it. So that now this, you might be asking at this point, well, all right, that's all well and good, and yes, we can see it's going to work. It will reset the Arduino or whatever microcontroller you have attached to the power output over here, over in this area. But why not just use an ATtiny13? And it's sort of a catch-22, isn't it? Because that was my first thought. Oh, we've moved on from 555s. We don't need those anymore. But a 555, as far as I know, does not latch up. No matter what you do, it just continues running forever. Whereas the ATtiny13 or 85, whatever, could latch up in the same way as the one you're trying to protect could. So if we were to put an ATtiny13 in here instead, and that latched up, we'd never know, because the power would stay on, we hope. And yeah, if anything happened then to the actual microcontroller that was doing the business, it would never switch off. So that's why it's good to have the 555, I think, at this point. Yeah, and I have a place in my heart for it, as I say, because I've used many a 555 in years gone by. If you're interested in 555s, and they are cheap, we'll have a look in a sec. There was an old book from Radio Shack, also known as Tandy in the UK, and we'll have a look at a little book there. And I had that book. I had his whole series of books, sort of about 5 or something, and it was really good. Let's have a look at, well, how much these things cost, because this is hopefully going to cost pennies to do, and then we'll have a look at those books with some circuits in it. Okay, first of all then, 555s. I haven't bought a 555 in so long, I can't remember. This is Banggood, and you can get 10 for $1.52, which is probably about, what, £1.30, I guess. Unfortunately, I bet there's shipping involved now. I'd found something on Banggood without any shipping the other day. I was stunned, frankly. But yeah, it was the only one thing I found. So $1.50, oh dear, oh dear. Shipping is more than the components, $2.08. Yeah, okay, well, there's always eBay, I suppose. You might find something locally if you just want the 1 or 2, maybe, in case you blow one up. But yeah, that's an option. Okay, what else does Banggood give us? Right, this is the SI4599. Once again, you can probably buy that reasonably locally. I don't think you'll get it this cheap, though. Now, I'm using on my smartphone charger the actual bare chip, because it's so tiny, as you can see from this board. Let's just fire this particular page up, and you'll see what I mean. You can see that the chip itself, look, is tiny, but the board they've mounted on here to make it, well, breadboard friendly, I guess, and, you know, hobbyist friendly, is huge in comparison. So if you can imagine that on a PCB, not the board, just the chip itself, the whole thing is going to be very, very small, I think. And for $1.98, once again, $2.09 shipping. I wonder if do they combine shipping on Banggood? If you were to buy the 555 and this, I wonder if they'd combine that, whether you pay them twice. Don't know is the answer. We'll have to find out, or somebody will. Okay, and finally, oh yes, 2N7000. Right, back to the previous page. Right, on this circuit, one of the things I have changed is this MOSFET here. I made it into a 2N7000 because I have a lot of them. Right, I've already got 20 or 30 sitting in a drawer up there, rather than the one that was specified on that circuit. And to be quite honest, any N-channel small type thing is going to work. This is a TO92 shape, so it's dead easy to use. You'll see it on the breadboard in a sec. So I guess it just doesn't matter that much. The only thing that does matter is the output MOSFETs. You do want them very low resistance, so the RDS on resistance must be low, and luckily the SI4599 is very low when it's on for the P channel. The N channel is even lower, but we're not really worried about that because the N channel simply turns on the P channel one. Right, back to the browser then. These are super cheap. As it says there, you can get 10 for $1.37. And no doubt it's going to be $2 shipping again, isn't it? I just think. Let's have a look. Yeah, $2.09. Well, I'd hope in some ways they'd combine that shipping, otherwise you're paying $6 in shipping there. Be interesting. I'll tell you what, I'm going to add these to my cart and just see what the shipping charge comes up as, and just put a picture right here so that you know. You'll know now if the shipping says $2.09 overall, or whether it's put it on as $6. If it says $2, great. I'd say, yeah, that's still good value for money. If it says $6 for those few items, no, we don't want them. Okay, what else can I tell you? Oh yes, the book. The book that I read all about the 555 back in about, I think it must have been about 1990 when I read this. So let me dig the page up on Amazon that are still selling it. Now in the UK it's hard to come by because after all it's an American guy. Quite an older guy now. Well, he was old then actually, so I don't know if he's older now. Let's bring that up. Now this isn't the best picture in the whole world, but you can just about see this notebook here. In fact, let me see if I can zoom in on this a little bit. Oh, there we are, there we are. That's better, isn't it? So Engineer's Mini Notebook, and this is all about 555 timers. And the guy who's done it is Forrest M. the third? Mimms? I don't know how to say that even. In the UK we don't have this nonsense about senior, junior, the third, Bill Gates the third, what? Son? I don't know. Anyway, so whoever this guy is, and he's quite old as I say, he wrote this, and it's like he's writing on graph paper inside. Very easy to read, and it's all handwritten. So yeah, if you want to learn about the 555, that is a good book. That's where I learned all my stuff on 555s. He does one on op amps and radio communications, stuff like that. There was quite a few actually. And it says here 4-star. I'd give it 5 myself, because for beginners it really is a nice little book. I can't show you inside the book because it won't let me flip into it, and I haven't got my copy anymore, or at least if I have, it's probably up in the attic somewhere. So yeah, maybe I should dig it out. I don't know. Right. Okay, just back to the circuit for a second then. The MOSFET is this one here. That's the 2N7000. I haven't got the SI459 not on here, but it doesn't matter. But I did say I was going to show you what it looks like on my phone charger one. So let me just show you the PCB for that, and you'll see how small it really is. So here's the PCB. Oh, it doesn't want to focus. And there, that's the chip, the two resistors you need, one from the gate from the N channel and one from the gate from the P channel. Or the other way around, that's the P channel one, that's the gate channel one. And that's it, that's all you need, those little 3 components there. Now these are through-hole resistors on this board, but with SMD of course they'd be much smaller. So I think I can compact that entire design into something quite a bit smaller. It's worth thinking about, isn't it? Great, I think that just about brings us to the end. Before you go, I've got a special little thing that will tell you, it's quite clever, that tells you pretty much where your next holiday could be. I know, it's absolutely amazing. So I'm going to drop that in now. You'll have to pause the video to read it all, but it's a nice little thing. You can do it with your kids again, all right? So I'll leave you with that. And if you like this video, please do give it a thumbs up. Lets YouTube know, and me, that you thought it was worthwhile. Comments down below for this video and the rest. And yeah, see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.